video is going to teach you about how to use the four constant acceleration equations of motion. First, I'll start off by giving you these four equations. Now, these four equations are probably the most important four equations you will learn in physics. We'll use them all year long, and it's very important that you understand how to use them. I suggest writing these equations somewhere where you can access them easily and quickly in class, because there will be several times throughout the year that you'll be looking for these equations. So maybe on the front of a notebook or on a note card that you can easily find and take out. The first equation is that the final velocity equals the initial velocity plus acceleration times time. Our second equation is displacement equals 1/2 the sum of the initial velocity plus the final velocity times time. The third equation is that the displacement equals the initial velocity times time plus 1/2 acceleration times squared. And the final equation is that the final velocity squared equals the initial velocity squared plus 2 times acceleration times displacement. We'll go through learning how to use these equations, but a couple of important comments first. You'll notice that in each of these equations, you'll see four variables out of a total of 5 possible options. The 5 options are displacement, initial velocity, final velocity, and time. In each case, there is something missing. One of those 5 variables is missing from these equations. This first equation is missing displacement. It doesn't appear anywhere in the equation. The second equation is missing acceleration. The third equation does not include final velocity. And the fourth equation does not include time. These missing variables will be key in figuring out which equation to use for a problem. One more important fact is that an equation we learned previously, the equation that velocity is displacement over time, can only be used if there is no acceleration or if the problem specifically says to find the average velocity over a time period. Okay, so let's look at a problem that'll use one of these four equations. Example number 12 deals with a golf ball rolling up a hill. It tells you to assume that the direction toward the hole is positive. The golf ball starts out with a speed of 2 meters per second and slows at a constant rate of 0.5 meters per second squared. We want to know the golf ball's velocity after 2 seconds. We're going to use the gummies method we learned in class, which means that I start off writing out what I know. So I know that the initial velocity is 2 meters per second, and that's a positive 2 meters per second because it is moving toward the hole, and it tells us toward the hole is positive. Then it says that it slows at a constant rate of 5.5 meters per second. This is negative, so that it will decrease the velocity. Lastly, we know that time is 2 seconds. All of my units match, so I don't need to convert anything. This question wants to know what is its velocity after 2 seconds, so it's asking for the final velocity. Looking at all the letters I have written up here, which variable is missing? If you answered displacement, you are exactly correct. So looking at my 4 equations here, I want to choose the equation that does not include displacement, which is the first equation. And so my next step is to figure out the model and the method that I'm going to use, and I figured out that the equation I want is V final equals V initial plus acceleration times time. I'm looking for V final. My equation is already solved for that, so I can go ahead and plug numbers in. 2 meters per second plus negative meters per second squared times 2 seconds. That gives me a final velocity of 1 meter per second. And it's very important you give me a direction as well. Not just simply saying positive is not enough. This is a positive 1 meters per second, and the problem told me that toward the hole is positive. So I will put toward the hole as my direction. That is a reasonable number. If I multiply it by 2, I get about what it is in miles per hour. So it's about 2 miles per hour, which is a very reasonable speed for a golf ball. Moving on to part B, it says, what is the golf ball's velocity if the constant acceleration continues for 6 seconds? So in part B, I have the same initial velocity, the same acceleration, but 6 seconds as my time instead now. I will use that same equation, v final equals v initial plus acceleration times time. My initial velocity is still 2 meters per second. My acceleration is still negative 0.5 meters per second squared. My time is now 6 seconds. This time, I get a negative 1 meters per second. When you give me your answer to any of these problems, I should see a magnitude, which is 1 meter per second, and then I should also see a direction away from the hole. I know that it's away from the hole because I got a negative sign on my answer over here, and it said toward the hole was positive, so the opposite would be away from the hole. That's a logical answer, and so I boxed it, and we are finished with this problem. Let's try another. In this problem, a skateboarder is moving at a constant velocity of 1.75 meters per second when she starts up an incline. It causes her to slow down with a constant acceleration of negative 0.2 meters per second squared. How much time passes from when she begins to slow down until she begins to move back down the incline? Okay, again, write out what we know. We know that her initial velocity is 1.75 meters per second. Her acceleration is negative 0.2 meters per second squared. And it says how much time passes from when she begins to slow down until she begins to move back down the incline. Well, her speed right before she begins to move back down the incline would be 0. The speed right before an object turns around is always 0. So even though the number 0 isn't given to us in the problem, it's something we know because she's turning around. My units matched, so I can move on to the next step, which is figuring out what I need to know. It says how much time. So I'm solving for time. Looking at the variables that are on the screen, which variable are we missing? Hopefully displacement was your answer. When I look back at my 4 equations here, the first equation again is the one that does not include displacement, so it's the equation that I will use to solve for time. V final equals V initial plus acceleration times time. I'm going to cross out that V final because I know that it's 0. So I'll cross it out with an arrow and a 0 at the end. I want to solve for time. So to solve for time, I need to subtract V initial from both sides, and then divide both sides by acceleration. So I get that time is negative V initial divided by acceleration, or a negative 1.75 meters per second, divided by negative 0.2 meters per second squared. Plugging that number into my calculator, I get a time of 8.75 seconds. That is a pretty reasonable time for her to start going up a hill and then start rolling back down. So I boxed that answer since it's reasonable. And now I will go ahead and move on to the next problem. In this one, we have a car accelerating at a constant rate from 15 meters per second to 25 meters per second, while it travels a distance of 125 meters. Let's know how long it takes to achieve this speed. Again, writing down what I know. The initial is 15 meters per second. The final is 25 meters per second. My distance, otherwise known as displacement in this case, is 125 meters. And all of those units match, so I don't have to do any conversions. It says how long. That means I'm looking for time. Which variable is missing here? If you said acceleration, you're right. Looking at my equations here, that second equation is the one that is missing acceleration. So it's the equation that I will use as I'm solving this problem. Delta x equals 1/2 v initial plus v final t. I'm solving for time, and so I'll solve that algebraically first by multiplying both sides by 2 to get rid of the 1/2. 2 delta x equals v initial plus v final times time. And then I'll divide both sides by that quantity in parentheses to get time by itself. So I get that time is equal to 2 times displacement divided by the initial velocity plus the final velocity. It's now time for me to plug numbers in. 2 times 125 meters divided by 15 meters per second plus 25 meters per second. You should get an answer of 6.25 seconds. Is that reasonable? Is it reasonable to go from 15 meters per second to 25 meters per second in that amount of time? Well, 15 meters per second is approximately 30 miles per hour. 25 meters per second is approximately 50 miles per hour. So going from 30 to 50 in 6 seconds is very reasonable. Once I check for reasonability, I can box my answer and know that I'm finished. That's the end of this video. We'll have some practice using these equations in class tomorrow and the next day.